All right, so welcome back to week 3 of software testing. I hope you enjoyed your early in the semester week off. A little too early for my taste, but it actually worked out okay for me. My father ended up in the hospital over the last week, so I was down in Florida, so it was okay. So anyway, let's pick up with where we are on the syllabus. So here we are on September 12th. We're in week 3. This week we're going to talk about test automation. And next week, Monday evening, start of class, assignment 2 is due. Assignment 2 is not very big. I did put it out there early in case anybody wanted to work ahead, but it really is based on stuff we're going to talk about tonight. But it's a pretty straightforward assignment. All right, so let's put that aside. Let's talk about quiz review. Actually, before I start quiz review, I do want to say my apologies for getting quiz 3 entered with the wrong due date. Several people saw it. One person took it, so congratulations to you for taking the quiz that you were not, you hadn't been through the stuff for yet. But that got pointed out to me and I fixed it. So I apologize if I made you all worry about, wait, how am I supposed to take this quiz? So, if in the future, if you see things that don't look right, do just, please point it out to me so that I can take care of it. All right, so let's go back and look at quiz 2. So distribution on quiz 2 scores. Yes, we're definitely heading in the right direction here, folks. Well done. And so let's take a quick look. We had definitions. There were several forms of this definition question, but basically they all boil down to the same thing. We're talking about the Ripper model. So in order to find a failure, the program execution has to reach a fault. That fault has to infect the internal state with an error condition. That error condition has to propagate to some observable point, and we have to have some test case or some test oracle that will reveal the error to us. I got a question in here. I wasn't taking synonyms for the question. Basically speaking, no, but if you've got specific questions about your answer, go ahead, and I'm saying this to everybody generally. If you have questions about how your quiz was graded, or you feel like, oh, I'm not really sure that this was graded right, please talk to Ridwan, our TA, first, because I've tasked him to do the grading, and I don't want to throw him under the bus here. If I'm going to give him the responsibility for doing the grading, I also want to give him the authority to do the grading. So talk to him first, and then the two of you can get in touch with me if you've got, if you've got issues that you can't easily resolve. All right, so then we had a couple of examples. This was one of them, given this software artifact. And I know that we haven't really talked about JUnit and our test automation tools yet. That comes today. At the same time, it's fairly obvious what this does, right? We're taking a list, we're adding names to the list, we're sorting the list, and then our test is checking to see that the first thing in the list equals Georgia. And so what's wrong with this test, or what are the shortcomings of this test? And the problems with this test is that the test is not capable of revealing, right, in terms of the Ripper model, the test doesn't reveal whether there are any potential problems with sorts after the first thing, right? This could be Georgia, Virginia, 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 and we wouldn't know. So that's the problem with this test. We had an alternate question. Given this software artifact, right, this fraction class, we have an add function. The point of the add function here, or the desired behavior of the add function, is to add the numerators if the denominators are the same, otherwise throw an arithmetic exception. And so what's wrong here? Or which of these tests, which of these tests do the following things, right? So which test doesn't execute the fault? Well, test 1, if we pass in null, that doesn't execute the fault, because here, if we consider the fault to be where we're adding the numerators, if we pass in null, that will throw a null pointer exception on the previous line, so the fault isn't reached. If we pass in test 2 executes the fault but doesn't result in an error. Why is that? Well, we're adding fractions that have the same denominator. So even though we execute the fault, it actually works the way we expected it to. It adds the numbers together just like we expected. So test 3 executes the fault and results in an error, but doesn't result in a failure. The reason for that is not so much because of how frac is written, but how the test is written. The test doesn't have any checks in it that would indicate that things went wrong. And then which test results in a failure? Test number 4 will result in a failure. All right, and then what everybody's been waiting for, where is everybody in the house cup? Muggles. Big points on Muggles last week. Muggles got a slide correction credit for calling me out on having the quiz with the wrong due date. I elected to treat that the same way I would treat any kind of slide error that gets reported to me. So the Muggles have kind of pulled out in front with Hufflepuff close behind, and we are early in the semester, and so this game is still wide open. All right, so with that, let's go ahead and get into our lecture content for today. So today we're going to talk about test automation. So if we go back to our model-driven test design, our flow chart, I guess I'll say, of all of our steps and our actions, our activities, we have the test automation activity here. This is what we're going to look at today. As I mentioned last week or last class, we're going to spend most of the semester up here in test design, but this week we're kind of taking a side trip here into talking about test automation. So what is test automation? When we're doing test automation, we're using software to control the execution of our tests, determine the outcome of our tests by comparing the actual results to our expected or predicted results. We're going to set up whatever test preconditions are necessary to run the test. We're going to have whatever other test control or test reporting functionality that we need. Basically, when our test automation runs, it's going to execute the tests, collect the results, and report those results. Why do we want to use test automation? There are lots of reasons. I think the heavy hitters are probably here. So first of all, this is going to dramatically reduce cost. Doing test automation, right? The act of creating test automation is more expensive than running a test manually. Depending on what resources you look at or what sources you look at, it's maybe twice as expensive or 4 times as expensive, something like that, right? We're certainly spending more time creating our test automation than we would by running the test. However, it's going to reduce cost in the long run because subsequent executions of the test, which basically costs the same amount all over again, right? If it costs me an hour to run a test manually, it costs me 10 hours to run it 10 times. If it costs me 5 hours to automate a test, it essentially costs me 5 hours to run it once or 5 hours to run it 10 times or the same 5 hours to run it 100 times, right? Running it is nearly, not entirely, but nearly free once I've written it. It's going to reduce human error. Human error is a serious problem in manually executed tests. People are not very good at doing the exact same thing over and over and following the exact steps. Most people find that boring, and they do what they think comes next rather than necessarily following what the test sheet says, and that tends to introduce error. And then if we have multiple individuals who are doing testing, we can get variations in their results, either because of differences in the way they're doing things or differences in the way they're recording the results. So we can get variation in our test results. It's going to significantly reduce the cost of regression testing. This is what I was talking about a moment ago. Regression testing is essentially a set of tests that we'll run from time to time just to make sure that we haven't broken anything in the system. If we're doing things manually, then from time to time might be every few weeks or every few months. But if we've automated our tests, then from time to time might be every night or every time somebody checks in a new change to the code. And so really probably the biggest key to the benefit of automated testing is that it's going to enable us to test much more frequently. And that's going to allow us to find defects much earlier, right? If we make a change to the system and a test fails tonight, I know exactly what changed. Okay, that must have been the thing I was working on yesterday, because that's the only change. Makes it very easy to go back and find and fix the problem. If we make 1,000 changes between now and December and then run our tests in December and 30 tests fail, now we have a big bug hunt on our hands to go back and try to figure out, okay, what changed, what caused this test to fail. And so it's going to allow us to do much more frequent testing to find our defects much earlier. Tonight's corresponding comment, our corresponding comic. This is obviously not what you desire, but it's also not entirely false either. Sometimes that automation does take more work and more maintenance than you might have expected. So let's cover a couple of definitions, because we love definitions, right? It's a graduate class, we have to have definitions. Software testability. Testability is a pretty simple definition. It's the degree to which a system or software enables itself to be tested, right? So how hard is it to execute tests and to find faults in this software? And that can be driven by a couple of things, but two of the key things that drive testability are controllability and observability. Controllability is the issue of putting the values that I need into the software, right? Providing the software with its necessary inputs so that I get it to do what I want it to do for the test. That sounds easy. And in simple software, it is easy. If I had a function that adds two numbers, I just call it and I specify the two arguments and it adds them. That's very high controllability, right? It just, whatever two numbers I give it, that's what it works on. But if we have a program that's perhaps very complex, it's got weather sensors, it's got, timing, right? Whatever it may have, it may be very difficult if there are many hundreds or thousands of inputs that are affecting this. How do I get the program to execute exactly the piece of code that I want it to execute with exactly the values that I want? And it can be very challenging in complex software. Our homework assignment number 6 at the end of the semester is going to have a significant, challenge, I guess I'll say, for controllability, right? It's going to be hard to make the software do what you want it to do. The second thing that really drives testability is observability. How easy is it to determine what the software did as a result of those inputs? Again, in trivial software, it's easy. If I'm trying to add two numbers, I say add 1 and 3, and it returns a value, and I check that the value is 4. That's highly observable. But I may have some state-driven system, right? Some system that changes its behavior based on what inputs it's gotten. I may have functions that don't have return values, right? They change the internal state of an object or a class, but they don't have return values. So if my function call that I'm testing changes private internal state, that's not very observable. I have to maybe go about it in indirect ways to try to figure out what the new internal state is of the software that I'm testing. So abstraction, when we're doing, data hiding, private members, abstraction reduces both of these things. So a lot of the things that you probably learned in your undergraduate, software studies, like data hiding, encapsulation, private methods, private variables, those are actually the enemy of testability. That doesn't mean you shouldn't do that, because it does make your program more maintainable and more reliable, but you end up having to balance these things. Okay, what compromises do I need to make in the purity of how I've written the software so that I can effectively test it. So there are some other things that can affect controllability and observability. I may need in my text some prefix, in my test, some prefix values. So prefix values are simply whatever set of inputs that I need to provide the system to get the system into the right state where it's ready to execute the test that I want to execute. Again, for simple software, go back to my adder. I don't need to do anything to the adder. I don't need to put it into a state. I don't need to make it add other numbers before I add my test case. I can just go directly. But if I'm, for example, testing maybe the anti-skid braking system of a car, I can't simply jam on the brakes. I also have to be going at a certain speed or simulate going at a certain speed. I have to hit the brakes with a certain amount of force, right? So there's a state that the car has to be in before I can run particular tests on the braking system. We may also have postfix values. Postfix values include the obvious verification values, right? If I'm running this test and I want to know what the result is, well, I have to have a predicted or an expected result. That's my verification value. I may also have exit values. Do I have some other statements, commands, inputs? Is there something else I need to do to terminate the program or to return the program to its normal state so that it's ready to do additional tests? And again, the more complex the thing that we're working on, the more likely it is that we're going to have these things, and the more complex these things are likely to be. So that makes a test case. What is a test case? A test case is an artifact that includes all of these things. It has the test case values, right? It has the inputs that I need to run the test. It also has the expected results. And it's also going to have whatever prefix values or postfix values that I need in order to make a complete test case. Then I can have a test set. A lot of people also call this a test suite, S-U-I-T-E. I use those terms interchangeably. You're free to use them interchangeably too. Test set, test suite, whatever. That's simply a set of test cases, usually somewhat related test cases that we've kind of put together into one package. And then we'll have an executable test script, and that is a test case or a test set that has been prepared in a form that we can automatically execute it and collect the results. So test automation frameworks let me build those automated test sets or automated test cases. So a test automation framework is basically just a tool that supports test automation. There are a whole bunch of them out there. Here are just a few, right? If you're writing Java, then most people that are writing code in Java are using JUnit as their automation framework. If you're writing C++, there are dozens, possibly hundreds. Google Test is a common one that's pretty well regarded. I use it for C++. I like it because there's a lot of information out there. It's pretty well documented, and it's really easy to go out to Stack Overflow and find an answer to the question without asking it. Or if you can't find a similar question, then ask it and get an answer, right? Because there's a lot of people out there using Google Test. Microsoft makes MS Test for C#. VectorCast is a commercial tool that's especially useful for embedded systems in C++ or Ada, which is another programming language that most of you probably aren't familiar with. Then there's a tool called Cucumber. Cucumber supports various languages. It's another open source and free tool. We'll take a look tonight at JUnit for Java, and we'll take a quick look at Cucumber as well. So what's JUnit? Well, open source software, so that's nice, right? It has a structure for writing test drivers. It's got a bunch of features built into it. It's got assertions built into it. Assertions allow us to verify that our software did what we expect it to do. We have test It's actually test fixtures. That's wrong here. It's correct on a later slide. Test fixtures that we can use to share common test data. If we have many tests that use, for example, the same setup data, we can set up JUnit so that we specify that once and don't have to specify it for every test. We can organize our test suites into various collections of tests of different sizes. We can run it from the command line. We can run it graphically through tools like Eclipse or Visual Studio Code. Very widely used in industry, almost certainly the most common testing tool used for Java. So where or when is JUnit useful? So we'll go back to this V diagram that we looked at, I think, last week. And again, this V diagram kind of implies this waterfall approach of we do all our requirements, then we do all our design, then we do all our implementation, then we test back up the other way. And we don't necessarily really develop code like that anymore and don't necessarily want to develop code. But it's still true that there are artifacts from each level on the one side that kind of drive what we're doing for testing on the other side. So JUnit is, for the most part, a low-level testing environment. So I'm going to use JUnit to do unit testing, for example, where I'm checking an individual class or individual methods of that class, or module testing, where I'm maybe testing a few closely related classes, or integration testing, where I'm testing how several different classes talk together. But I'm probably not going to use JUnit for the system testing level or the acceptance testing level, where we're verifying whether the software does something that's useful for the users. JUnit is really not the right tool for that job. We'll come back a little bit later tonight and talk about what is. So when we're testing in JUnit, we can test an entire object. We can test part of an object, one method, multiple methods. We can easily test interaction between several different objects. This is where JUnit really works well. So each test that we want to write is embedded into one test method. So when we write a test in JUnit, that test is itself a Java function or method. And then we can collect those into a test class, and that test class will contain one or more of those test methods. If you go to junit.org, you will find everything you need. You'll find the downloads, you'll find instructions, there's user manuals, there's examples, there's lots of stuff there at junit.org. My slides are using JUnit 5. You've got an opportunity here to perhaps find some slide errors because I just upgraded this semester from JUnit 4. You could easily be asking me what took you so long, but once you get used to a framework, you kind of stay there until somebody forcibly kicks you out. So I just upgraded everything to JUnit 5, which means that maybe there's errors in the slides. So when we're writing tests with JUnit, we're going to largely use the methods that are specified in this org.junit.assert class. And there's plenty of info in there, right? There's a lot of information that's built in. But each of these assertions checks a condition and reports to the test execution whether or not that condition was met. And if all of the conditions are met, then the test passes. But if any of those asserted conditions are not met, then the test fails. And then the test runner will use that to report to the user, either in command line or update the IDE in Eclipse or Visual Studio Code to show us what the results were. All of these assertion methods return void. There are a lot of them, but here are a few really common ones. So we can have an assert true, where we have some expression that evaluates to a Boolean result. And if that expression evaluates to true, then this passes. If it evaluates to false, then it fails. Assert false is exactly the opposite. If the expression evaluates to false, then the assertion passes. We can have assert equals, where we have an expected value and then an expression that can be numeric, it can be string, it can be lots of things. And again, if the values are equal, then the test passes. A very closely related assertion is assert near. With a certain year, we're giving it an expected value and then an expression and saying, this test should pass if the expression is within some delta value of this expected value. We particularly like to use that on floating point comparisons, because hopefully we all remember, going back to undergrads, that it's usually a bad thing to test floating point values for equality, because floating point numbers are approximated numbers, and it's very easy to have numbers that are very, very nearly the same. For all practical purposes, they're the same, but they're not exactly the same. We can assert if something's null. We can also assert if something's not null. And then if we want to, this is sometimes handy, we can simply cause the test to fail. And you're thinking, why would I just want to outright cause the test to fail? One reason might be I haven't implemented the test yet, right? But I know I'm going to need it. So let me just write it now. Let me just put it in there and say that it fails. That way, all my tests won't pass and I won't think that I'm done. Another reason might be we've got some logic, right? Some more complex logic than I might want to do in these other simple assertions. And if I get to this point in the logic of evaluating the results, if I get to this point in the logic, then I know things went wrong and I should just fail. All of these assertions, as you can see, they can take an optional first argument, and that optional first argument is a string that will get printed out if the assertion fails. And that can be really handy for when you're doing traceback, right? If you not only know that this assertion failed, but it failed, and then here's a message that the developer wrote in there for why that might have failed or what it might mean for that to fail, that can be a very useful thing to have. So I've got a question in the chat. Is JUnit 5 backwards compatible? Mostly. There are a few differences. The typical assertions are all backwards compatible, and you can actually run under JUnit 5 using JUnit 4 functions, and it'll accept that. But there are also some differences. There are some things in JUnit 4 that aren't supported in 5, and vice versa. And yeah, I don't love the failure message being the first argument either. And then somebody else is telling me, oh, in JUnit 5, the failure message is expected at the end, not at the beginning. That's interesting. If that's true, I feel like that actually makes a lot more sense. So, you may have caught me on this one, and then here just one slide later, I'm already caught up on, I'm already caught out on a possible slide error. So good, I'll check into that. So let's look at a simple JUnit example. If we've got this class calc, it's got an adder in it. It adds A and B, it returns the sum of the two. This is a pretty simple piece of code. What might my JUnit example look like? Well, I've got to import a couple of things. Then I have a class, that's my test class. And then my test class has a test method. It starts with this @test annotation, then public void, and then some name of something. Typically naming conventions will be, I'll usually name, or people will usually name the test class to be the same as the thing that they're testing with a test on the end. So if you're testing calc, then your test class is calc test. And usually if you're writing test functions like this, usually your test function will be the same as the function you're calling with a test, at the beginning or at the end, whichever way you prefer. So I've got this test method, and this test method, this has a very simple assertion in it. And we're just asserting that when I call calc and I ask it to add 2 and 3, that the result is 5. And if the result is not 5, then it'll print out calc sum incorrect. And okay, yes, going back to JUnit 5, maybe that wants to be at the end. Thank you for the link. I'll look into that. So pretty simple test example. I do want to point out that on future quizzes, including this week's, you're going to be asked to write JUnit tests. You don't need to worry about all the assertions and everything else. I'm not going to copy your code and try to compile it. When I'm asking you to write tests, JUnit tests in, in quizzes, really I'm just kind of caring about the guts right? I don't need the class defined. I don't need all the imports. Just really kind of asking you to provide what the guts of the test would be. What are the assertions or what are the data setups? So although this is a very simple example where we kind of roll everything together and do it all at once, more generally, a JUnit test kind of has three sections. The first section will be to do whatever data setup we need. And then the second section is to call the thing that we're testing, right? To make that function call or function calls. And then the third part is to execute the assertions to verify that the results were what we thought they should be. In this simple case, we've really rolled all that together, right? Here are the inputs, here is the call, and then the assert equals is the verification. So that's pretty straightforward. Let's talk about a few other things that JUnit can do for us, some things that are, maybe a little more interesting. First of all, we can have JUnit test fixtures. A test fixture controls the state and the execution of a set of tests. And so if we have objects or variables or data structures that are used by more than one test, right, more than one test method, like initializations, prefix values, right, things that I need to put the system or the software into the right state, or reset values, things I need to do to clean up after the test executes. I don't have to write those individually into every test. I can write them once, and JUnit will essentially, run them like function calls. So I can initialize things. I can set up that initialization in JUnit with an at before each or at before all annotation, which will cause it to be run before each test method or once before all the test methods. And then I can have cleanup, and my cleanup can be set up to run after each test method or once after all the test methods. So it's very flexible. So let's take a little bit more detailed, example look at writing a JUnit test. So we've got this min class. So we've got method details coming up next, but what is min? Min simply is going to take a list, a templated list, don't care about the type, and it's going to return the minimum value, the minimum element in that list based on whatever the comparator for that type is. And it's going to throw null pointer exception if the list is null or if any of the list entries, any of the elements are null. It's going to throw a class cast exception if the list elements can't be compared together. And it's going to throw an illegal argument exception if the list is empty. So let's take a look at the method details. So here's what min looks like. So we check to see if the list size is 0. If it is, we throw an illegal argument exception. Otherwise, we create an iterator, we grab the first thing off the list. If the result is null, right, the first element is null, then we throw a null pointer exception. Then we iterate through the rest of the elements in the list, calling the comparator, doing a compare to, finding the minimum thing, and then eventually returning the minimum element from that list. So pretty straightforward. So what's our JUnit test going to look like? Well, we're going to include a bunch of imports for JUnit classes. We're going to include assertions. We're going to include after each and before each. We're going to include the JUnit test structure. We're going to have some prefix setup. So this is not very complicated setup, but in our test class, we're going to define a private member that's a list of type string. And then before each test method, we're going to run, or JUnit will run for us, because we've said before each. JUnit will create a new empty array list and assign it to that variable so that we know every time we call a test method, that test method is going to have a nice, clean, empty list of strings to work with. Then we're going to have a teardown, right? After each method is called, we're going to take that list and we're going to set it to null. that doesn't really do much for us. I've really included it in here just as an example. So now let's go through a process, and I'm going to call this process intuitive test case development, right? We're not using any particular set of rules. We're not using any particular test criterion that we're going to talk about later. We're not really trying to achieve statement coverage or branch coverage or specifically. We're just going to kind of go through this code and think about, well, what could happen at each stage? And maybe we'd like to have a test for that. So if we look at this code, you know, when we consider, all right, we enter at the top, what do I care about? Well, okay, first thing I care about is this a null list? Because if it's a null list, then that's going to throw null pointer exception. Well, if it's not a null list, is it empty? Because if it's an empty list, then we're going to throw illegal argument exception. What about the first value of the list? If the first value of the list is null, we're going to throw a null pointer exception. So that seems like another thing to test. Or the first value isn't null, but what if there's only one element in the list? So we were able to extract the first element, but when we go into the iterator and check to see if the iterator has next, there is no next element. What does that behavior look like? What if there is a next element, but it can't be compared to, right? Because it's an incompatible type, so the types can't be compared. What if there's a null value later in the list, right? We checked for a null value in the first element of the list. What if there's a null value in some later element of the list? What about a test where we compare our current minimum to the latest value, right? The latest value in the list, the latest element in the list, and we decide that the previous one is the minimum, and so we keep it. Or alternatively, what if we decide that the new one that we're comparing is the minimum value, and so we need to keep that one instead? All right, so those are all test cases that we can kind of intuitively see by looking at the code. All right, that looks like it might be an interesting thing to test. If we did all these things, you know, did we achieve statement coverage? I don't know. Did we achieve branch coverage? I don't know. We've probably done pretty well, right? We've probably gotten fairly close, but we're not really caring right now about any particular coverage criterion. We're just trying to walk our way through here and see, you know, what are the test cases that occur to us? There's a question in the chat about whether the third null check is really necessary. And yeah, it may or may not be, but this is kind of simply the example code that I picked out that we're working with.
So this is supposed to be an incorrect example?
The code?
Yeah.
No, the code's possibly fine. You know, I'm going to leave it open as to whether you think there's a problem in it. But this is just an example of code that we're kind of going through. What's an intuitive process to develop tests from this? And then what I'm leading up to is, what would those JUnit tests look like, right? When I implement those tests, what are those tests going to be?
And for 0.5, how would it be incompatible when the entire list is supposed to extend comparable?
So right now we have a list of strings, right? So I can't have two strings and have them not be comparable, but maybe there's another thing I can do. So keep that thought and we'll come back to it.
Well, the top of the argument, yeah, the top of the method, the arguments with the type parameters, I don't see how that would be possible, that they're not comparable. Or maybe it's just me not understanding the Java generic typing there.
Yeah, okay. So because T extends comparable, you're saying?
Yeah.
So in all honesty, I'd have to go back to this and study that syntax myself. But I do have an example that I ran that does fail this.
Okay.
I think it allows you to use raw types, which is a problem.
Yeah. All right, so let's look at some test examples. So our first test here was a null list. So if I wanted to write a test with a null list, what would that test look like? So here's an example. We're going to assume that we have an enclosing unit test class already. So I'm just looking now at our unit test methods. So at test public void test null list. So I gave it some somewhat meaningful name, right? It's clear from the name what we're doing. So I need to set the list to null because that prefix setup that we had, that at before all, that was going to set list to be an empty list of strings, an empty array list. So I need to reset that. I need to reset that, force it to null. And then I'm going to call min.min and pass it in list. And what I'm expecting it to do is throw a null pointer exception. So if it throws a null pointer exception, I catch it and return, and this test passes. If it doesn't throw a null pointer exception, then we skip over the catch and we come down, and here's an interesting case, like I was talking about earlier, where fail is useful, because I've kind of built my logic such that if execution of the test gets to this point, then the test is broken. So there's our first test on a null list. What if we wanted to test an empty list? Well, our at before all has already created me an empty list of strings, so that's not tough. So I can use this JUnit 5 notation. And honestly, I liked the JUnit 4 notation better. I thought it was a little clearer, but I'm going to go with the JUnit 5 and basically say this assert throws. So I'm saying here, I'm asserting that this thing that I'm calling, min.min and pass it list, should throw an illegal argument exception. And if it doesn't, then the assertion fails. If it does throw that exception, then the assertion passes. So these two approaches are doing exactly the same thing. They are passing, yeah, what's with the funky lambda looking thing? Yeah, I'm not loving this syntax, right? It's just kind of odd. But these two things do exactly the same thing, right? In both cases, we're calling min.min, and if it throws the expected exception, then the test passes. If it doesn't throw the expected exception, then the test fails. Either of these are perfectly acceptable approaches. Honestly, I like the first one. I feel like the first one is very, very obvious what's happening. I don't need to know anything special about what's this arrow thing and why is that in curly braces. It's just pretty, okay, yeah, I put it in a try catch, I called it, it didn't catch what I thought, so it's broken. But both of these, totally acceptable. They do exactly the same thing. The rest of my examples are going to use this, the rest of my examples here in this slide set are going to use the second one simply because it takes up less space on the screen. All right, so I wanted my third test to test what happens if I have a null value as the first element of the list. So I'm going to take my list, which is a list of strings, right? That was an empty list of strings that was prepared for us in the at before all. I'm going to add a null, and then I'm going to add a string. And then I'm going to call min.min, and I'm asserting that that should throw a null pointer exception. And if it doesn't, then the test fails. Fourth test case, test a list with one element. So I have my empty list of strings out of the setup. I'm going to add a string. I'm going to call min.min, and the object that I get back should be equal to what I put in. What about a list with more than one element that has an incompatible type? So here we are back to Kyle's earlier question. So I can't do that with an array list of strings because strings are always comparable. But I can reset list to be an array list of generic types. And then I can put in a couple of strings and I can put in an integer. And then when those try to compare, that will throw a class cast exception. And again, my assertion says I expect a class cast exception. And if that doesn't happen, then fail the test. Then we had our test number 6 to test a list that has multiple elements, that has a null value that's somewhere that's not the first element. So I can take my empty list, I can add a string, I can add null, and then I expect that that will result in a null pointer exception. In our 7th, we want to test a list with more than one element where the minimum element is first, so that we're always keeping the previous result. So I'll add three strings and I'll just set the first one up to be the minimum value. And then I'll call min and I'll assert that what came back out of the call to min was that expected minimum value. And then we're going to test the list with more than one element that has the minimum element later in the list so that it has to do that swap, right? It has to reset result in the code. So I just change my order around and I move my minimum one to not be the first thing. Call min and then check that that's what comes back from the test. So the interesting thing here, or an interesting thing, we identified 8 tests. 5 of those tests expect exceptions to be thrown. Only 3 of those tests are what you would really generally consider normal execution of the software. And that ends up being pretty typical. We will often have more test cases that cover things that go wrong, or things that can go wrong, or things that are not what you normally think to be. This is kind of the normal way it should run. And relatively few test cases that actually look at what the normal execution is. So we talked a little bit about test fixtures before. When we were talking about test fixtures, that was kind of organizing all our setup stuff and our teardown stuff so that it's run for every test. We can also have parameterized tests. It's pretty often that we're going to want to run tests where we're going to call the same method many times with different data values. So if we have this adder again, right, add I and j, I could write a bunch of tests here. And I could say, you know, assert that add of 1 and 1 is 2, and assert that add of 2 and 3 is 5, and assert that add of 5 and 10 is 15. And I could do that on and on and on. That gives me a bunch of code, duplicated code, really. Those testing adder is very simple, but if I had something a little more complex, you could imagine that I've just got a bunch of duplicated code for all these test cases, and I'd like to eliminate that duplicated code. Parameterized tests let me do that. In parameterized tests, I have a little bit of a different tag on my class. This tells JUnit, hey, this is a parameterized test. What's a parameterized test? In a parameterized test, I'm going to write the code once, and I'm going to write it using essentially arguments. And then I'm going to tell JUnit, and here's all the data that I want you to use. And I'm going to give it a list of lists where each element in the list has all the necessary arguments. So now I have the code written once, and then I give it a big collection of data, and then JUnit will automatically iterate through that set of data and run the test the proper number of times, once for each set of data that's in there. So I've got a question in the chat. How many of each type of test should we make to ensure our code is tested properly? Is one test testing a null list enough? So that's a good question. And that really, that question is why we have test criteria, so that we can use the test criteria to tell us how many different tests we want to have. In this case, is having one test with a null list enough? Well, having one test with a null list is no different than having another test with a null list, right? Because there's only one definition of null. So having multiple of those wouldn't really help. But for example, if I have one test where I return the first value, do I need another test where I return the first value? Maybe, probably not, but what are we trying to prove? Are we trying to execute all of the code? Are we trying to execute all of the branches? Are we trying to execute everything that's in the input space? So those types of criteria can help us decide how many tests we need and what those tests should be. In this example, we were kind of using an intuitive approach, right? So we were purposely putting criteria aside. I don't care about the criteria right now. I just want to kind of walk through and do kind of a gut feel set of tests. All right, so we were telling JUnit that our test was parameterized. Then we've got member variables to hold the test inputs and the expected output. So the two test inputs and the expected output. Then we have a constructor that creates an instance of this class and initializes those test inputs and expected outputs. And then we have the definition of all of the test cases. So test input, expected output. Test input, expected output. And this could go on arbitrarily long. And then we have the actual test method. So the test method, this is what's going to automatically get called once for every set of data here, and it's going to operate on I and J and compare that to sum. So what JUnit's going to do, it's going to take one set of data, it's going to call this constructor. This constructor is going to push those values into I, J, and sum. Then it's going to run the test, and the test is going to say add of 1 and 1 is equal to 2. Yes, it is. Test passes. Can you do parameterized tests and normal tests in the same class? Yes, you can. And I don't think it'll break, but I would probably split that into two classes just to kind of keep everything nice and neat and clean. All right, so we talked about unit testing, module testing, integration testing, places where JUnit is a good fit, right? Low level, working directly with the code, that's what JUnit's good for. What about when we're doing system testing or acceptance testing? Now we're testing at a high level. I don't really care about the code. I don't want to care about the code at this level. I want to be a little more abstract about showing that the system is doing what I expect it to do and what we desire it to do. If I can't use JUnit here, or if JUnit isn't a good fit here, what is? Yeah, all right, so JUnit is not a good fit, right? Too technical. Your systems engineers, your system architects, your customers, be they internal or external, they are generally speaking not going to want to look at JUnit tests, right? That's not the world that they live in. They're like, yeah, that's that software stuff that you guys take care of. I don't want to think about that. So JUnit's not a good fit there, right? And JUnit's not really designed to interact with an entire running system. It's designed to run particular classes and functions for the most part. So we need a different test automation tool, one that's more appropriate for acceptance testing. Cucumber is one of those acceptance test or system test level tools. There are a lot of them out there. They tend to have strange vegetable names. Cucumber, radish, lettuce. I don't know why I didn't make them all up. But Cucumber is probably arguably the first and probably the most commonly known. All of them are pretty similar. So we're going to write system level tests, but we're not going to write them in Java, and we're not going to use JUnit or JUnit assertions. We're going to write them in a language called Gherkin. And Gherkin is an English-like or a natural language-like test specification language. I say English, but actually there are versions that will allow you to write things in other languages as well. The fact of the matter is that the tool doesn't really care what language you used. One of the benefits of these Gherkin tests is that they can easily be written by people who aren't developers, right? So you do not need to be a software developer, a software engineer, programmer, tester, right? You do not need to have that technical knowledge in order to write Gherkin tests. That leads to this very nice example that customers can understand the tests. Kyle is reading ahead. I'll come back to that. Customers can understand those tests that are written in Gherkin. So that gives you and your customer or your product development staff or your product owner or whoever you might be working with, that gives you kind of a common ground to talk about and develop an understanding of what the system should do and how the system should work. So what does Gherkin look like? A Gherkin test specification consists of 4 sections. It's got a scenario section. The scenario is just a short description of the functionality under test. The scenario section is documentation. Then it has a given section. The given is a precondition for the test. When I say given blah, 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 what I'm saying is that's the state that the system needs to be in order to run this test. Then there's a when specification. The when specification specifies what's the input or what's the stimulus, what's the thing that causes the initiation of the test. How do we initiate the test? And then there's a then section. The then section contains the post conditions or the expected results. Essentially, it's like JUnit's, okay, brain fart, word. Assertions. It's essentially, yeah. You could also have postfix here, but what I was looking for was it's essentially like JUnit's assertions. This is where we determine whether the test passed or not. So we're going to write these tests at a much higher level of abstraction, right? We're going to write it at a level of abstraction that users, customers, system engineers, management, right? People that aren't the software development team can understand. So let's look at a couple of examples. So imagine we have an online ordering system. We want to write some Gherkin tests for our online ordering system. What are some tests? Well, okay, we have a customer login scenario. And the definition of that is the customer logs into the account and is directed to his or her account. Okay, fine, a fairly high level description, but okay. And what might that test look like? Well, given that the ordering system is running and the customer is on the login page, those are the preconditions. We have to get there one way or another. We have to get there in order to run this test. When the customer enters the correct username and password, that is the thing that initiates the test, right? That's the action that initiates the test. And then what do we expect the outcome to be? We expect that the system will validate the login and the customer will be sent to the shopping search page. Okay, now they're logged in and now they can go and find things to shop or shop for. We might have another test about adding an item to a shopping cart. And the customer selects displayed item, adds it to the shopping cart. Okay, so we have some given, we have preconditions. We need the ordering system to be running. The customer now has to be logged in and the customer has to be viewing some item, right? And here I've identified that item numerically, just for an example purpose. What initiates the test? When the customer selects add the item, the system will do its thing. And then the expected outcome is that that item is added to the shopping cart and the order total is increased by $14.99 because that's how much we know that item costs. And the customer is given a choice to check out or continue shopping. So those are two fairly simple Gherkin test examples. So coming back to Kyle's statement, this kind of looks like magic. Okay, well, how is the system supposed to know that the item is added to the shopping cart? And how is the system supposed to know what it means that when the customer selects add item? That seems like magic. Well, as usual, there is no magic. There's just more detail that underlies this. So what's underneath all this? What's underneath all this is Java code and, perhaps not surprisingly, JUnit code. So we have these additional tags that we use when we're writing code to support these Gherkin tests or these Gherkin statements. So we have this @when that tells Java this function, this method is going to handle a when statement. What when statement? Well, when the customer enters a correct username and password. So that's what this statement is doing. All right, what does it mean for a customer to enter a username and password? Well, if we're going to automate that, then we might say, well, we're going to go to the agent that allows us to interface with the graphical user interface, and we're going to set the text field username to johnsmith@test.com. And then we're going to go through that agent that allows us to talk to the user interface, and we're going to set the test field password to test password. And then we're going to go through that agent that allows us to talk to the interface, and we're going to select the button that says login. And that's how we have built a low-level implementation of that high-level English-sounding Gherkin step. So we might have another example here. This function is going to handle, then the system validates the login. It's also going to handle, then the customer is logged in. And if you're looking at this little vertical bar here, if you've got regular expression experience and you've done a little work with regexes, you may be thinking, oh, that kind of looks like a regex or, and that's exactly what it is. This string after the when or the then or the given, that string is a regular expression. And any Gherkin statement that matches that regular expression will be handled by this function down underneath the covers in the implementation. So what does it mean for the system to validate the login? It might mean that we go to the authentication agent and we get a list of validated users, and we assert that that list of validated users includes John Smith. There may be any other kind of implementation, right? This is simply an example implementation, just to show that, or just to show the mapping between, we have that high-level statement in Gherkin, back here, and then given the when, the then, the customer is logged in, the customer is on some item page. Well, that's not magic. It maps back to a Java function that will do something to interface with the system to determine if that's true or to take those necessary actions. So those steps in Gherkin actually end up being JUnit tests. Is there a notable difference between the different annotations? Can you elaborate, Kyle?
Well, for example, you could just all write them as when, and it would still run the same.
So technically, the current implementation of Cucumber, you could. There is no difference between them in, well, I should say the 2-year ago implementation of Cucumber, because that's really the last time that I worked with it. There's really no functional difference. It'll just run them all. But the given, when, then is really a tool to allow you to structure these tests at the human readable level.
Okay.
So we can also take arguments. So here we have when the customer is on item page and again, this is a regular expression. So what we filled in here is this will match any text that says when the customer is on item page and then some number. And as long as there's something, when the customer is on item page 1, that'll redirect here. When the customer is on item page 99, that'll redirect here. And it'll take that number and it will pass it as an argument into this function. And then we can use that however we want to use it in the code. So again, it's not really magic in any way. It's just taking that English level definition, it's parsing it, it's trying to match it against regular expressions, pull out the parts that you may have specified as arguments, and then pass them in. In the add item to shopping cart, if we have a dynamic price, how would the Gherkin specifications change to accommodate that? I would suggest that for your test cases, you probably would not have a dynamic price. You would probably set up your test with a specific price and make sure that that's what the system did in that case. Because if you've got anything non-deterministic, then your tests become very, very difficult. It becomes very, very difficult to verify that your test did what was expected if the results are not deterministic. Sometimes the results are not deterministic. So imagine you are writing a game and the game is simulating the roll of dice. Well, the roll of dice is kind of the ultimate classic non-deterministic thing. And you might need to run a test to show that the roll of your dice is not deterministic. Well, you probably are going to have to do a statistical analysis on that, right? I rolled it 1,000,000 times and I expect approximately 1/6 to be 1 and 1/6 to be 2, 1/6 to be 3. But you've really kind of gone into another more complicated space when you have things that aren't constant. So anytime you can use constant things, that's what you want to do. So I talked about agents, we talked about step definitions, we talked about Gherkin. How does that all go together? And basically, you end up kind of at that top level, that most abstract level. You have your Gherkin statements, right? Given that the customer is logged in, when the customer picks buy now, then the item is added to the cart, right? Those are all of these test specifications in Gherkin. Then below that, you've got your step definitions that are written in our example in Java. And that's where we're actually making something actually happen. And then you may have this fourth agent, right? Or this fourth level, excuse me. Third level, I can count. You may have this agent level in here. The agent level is just an abstraction layer that lets you talk to the system under test. You might decide to skip that and talk directly to the system under test from your step definitions. That's fine. The bigger your system is, the more complicated your system is, typically the more useful it is to have an abstraction layer in between there so that different Cucumber tests can reuse that code to get at the system. But this is really where we're going from most abstract, right, our English language test definitions into the Java definitions, and then perhaps going through some agent to get to the system, and then finally talking to our implemented system. No magic. So quick summary for tonight. If we want to make our testing as efficient as it can be and as effective as it can be, then the way to do that is to automate it. Test frameworks like JUnit, Cucumber, many others provide us with relatively simple ways to automate tests. And the key thing here is they let us focus our time as engineers on things that are high value, right? We get to spend more time thinking about test logic. What should I be testing? What criteria am I trying to satisfy? What should my test values be? And we spend less time thinking about low value stuff like, oh, I have to compare these values. I have to somehow report this back, that if any of them aren't right, then I have to report back that the test failed, right? The test framework takes care of those simpler things for us and lets us spend our time on high value work. But there is a substantial limitation to test frameworks. Test frameworks can't tell us what to test. They don't tell us what functions to call, and they certainly don't tell us what the values should be. What are our test inputs? Test frameworks can't tell us that. So that's the purpose of test design and using test criteria. And so we'll start talking about that next week or maybe the week after. I think it's week 5. We start diving really into test criteria. So test frameworks, great tools to help us with the test implementation, but we still have to do all that work in the background for test design and working to satisfy our selected test criteria. All right, welcome back from break. So we're going to get on with our class exercise tonight. And this is going to be in 2 sections. The first section is going to be a JUnit exercise. Second section is going to be a cucumber or gherkin exercise. So there may be some confusion because I've used cucumber and gherkin, and then I've kind of talked about one thing. And I frequently get asked, okay, wait, what's the difference between cucumber and gherkin? The answer is that gherkin is that definition language. Scenario, given, when, then. That language to define tests, that is the gherkin language. Cucumber is one of several tools that will process that language and map it to underlying code that will actually implement it. So cucumber will map gherkin to either Java or I think Ruby. Lettuce will map it to, now I forget, Lettuce might be the C++ tool. Now Radish, I think, is the C++ tool. But there are other similar tools that will map gherkin to a different underlying implementation language. So gherkin is the test definition language. Cucumber is the tool that executes it. All right, so with that said, let's go ahead and move forward with our exercises for tonight. All right, so this file is available on in week 3 on Blackboard. So we've got a point class. Here's the point class. A point has an X and a Y value. It's got a constructor, and then it's got a Boolean function equals. So we pass in some other object, and the question is, what should this implementation do, and how should we test it? So we're going to have 4 pieces to this, 1, 2, 3, 4, or perhaps 5 pieces to this. So the first question is, what should point.equals look like? So as your first part of your task, fill in a potential implementation for point.equals. Yeah, so given something like this, right, what is this code? Next, provide some JUnit tests for point.equals. If I wanted to test equals to make sure that it works, using kind of an intuitive approach like we talked about earlier in the example that we had for min, right? Following some intuitive approach, what do I want to test for equals and what would it look like? And don't focus on like all the imports and everything else. I'm mostly interested in your data setup, your execution, and your assertions. So if you've got, here's the data, here's what I called, here are the assertions that I ran, I'm going to consider that to be complete for our purposes. The homework assignment is going to have you actually implement some, and obviously for the implementation you have to do everything in the right syntax and have all the imports. But for doing it by hand in this exercise and in the quiz, I don't need all that detail. So what does test equals look like? And then if you wanted to write a parameterized test for point.equals, what would a parameterized test look like? And again, a parameterized test, if we go back to the example we had, that's one where we write the code for the test once, and then we write a set of data that JUnit will automatically iterate through. Right? It'll automatically iterate through that data and execute the sample test once for every set of data that we provided. All right, and we filled in some things here. And then this part, test theories. Not doing that. We're taking that out. Okay, we didn't talk about that. That was a feature of JUnit 4 that is provided in a different and more complicated way in JUnit 5 that wasn't worth doing. So skip the test theories. And there will be no test theories section on the quiz. So never mind that. All right, so what does the implementation of equals look like? Develop some JUnit tests, develop some parameterized tests. This can be different tests or it can be the same tests in a parameterized format. I don't care. Skip the theories and then we'll be back here. So I'm going to set us up for 20 minutes on this and then we'll all come back and we'll go through our, I'll have each team do one part of this. And yes, I know there are more teams, but that's okay because there's a second section of exercises. So, any questions before we launch? All right, 20 minutes, and then here we go. Let's go around and see what we've got. So, I've got a little, random number generator every week that sets the order of who we talk to. So we're going to start off with the Hufflepuffs tonight. So Hufflepuffs, can you show us your implementation of point.equals?
I guess we can verbally describe it. I hadn't written anything down, so I guess
okay.
In the future we can try and better prepare by writing it like on something.
Okay.
But equals, you would first do a type check. So it would just be so if object O is an instance of point, you continue on, otherwise return false. And inside that if block, you just do a cast from object to point and just get its values and just compare those values and return whatever Boolean you get.
All right, so let's take a look at my example. And I think this matches what you just described pretty closely. So we take in an object, we check to see if object is an instance of point. If it isn't, we return false.
I cannot see your screen.
Oh.
Yeah.
All right, one moment. Oh, there it is. How about now?
Yeah, now we can see that.
Okay, great. So I think this is what you were just describing, right? You take the object O, instance of point. If it's not a point, return false. If it is, cast it to a point, and then verify that this X is equal to the other X, and this Y is equal to the other Y. So good. That's pretty much exactly what you explained, I think. So that looks good. So, this is not an overly complex, not an overly complex function. So good job. All right, so let's move next to.
Quick question.
Sure.
We had someone in our group bring up like the point of like having null as being passed in an object.
Mm-hmm.
Would that and then we chose to go with throwing an exception in that case. Should that not be the case? Like, how do we decide?
Given this code, how would you get a null in?
Like if O was null, like do we want
If
to?
O was null, okay. So if O is null, then what'll happen with this code?
It should return false, right?
Well, if O is null, this code will probably throw a null pointer exception, right? Because it's going to try to figure out what type O is. So it's going to, it's not explicitly dereferencing O, but I'm reasonably sure that calling instance of on a null is going to cause us a null pointer exception. So is that good or bad? Let me ask you. If we pass in a null and this throws a null pointer exception, is that the desired behavior or not?
I think it would be a desired behavior.
So I
right?
just checked Stack Overflow and it says instance of will always return false apparently on a null object.
Instance of will return false on null. Okay. Well, then in that case, we're back to your original statement that it would return null. So, okay, good. Thanks, Kyle. Appreciate that. So either, really either behavior, neither behavior would be wrong. I mean, I was asking you which way you thought it should go, and it was a little bit of a trick question, because either answer you gave could be right or could be wrong, because we don't have any desired behavior specified, right? There was no specification in here about what should happen. Now, generally equals as a function we're overriding, equals probably shouldn't throw an exception because we wouldn't normally expect that to happen by calling equals. So the outcome of this will return false if it's null, that's probably a better outcome, but it's hard to just clearly say, boom, one is right and one is wrong. And I'm missing a closed parentheses in my example too. All right, great. So let's go on to our next group. And next up, we're going to go to the Ravenclaws. So Ravenclaws, what do you have? Let me stop sharing so that you can share yours. What do you have for point.equals unit tests? We got any Ravenclaws out there that want to share?
Hello, give me a moment.
All right.
So we got as far as like listing out the tests that we would write, but not actually writing them. So we have one to check for when the point is a null object, one to check if the object inputted is of type points, test for if x and y are equal for both points, check to see if x is equal or not equal, check to see if y is not equal, and check to see if both x and y are not equal.
This is really good. Okay, so you've really kind of given a set of test requirements rather than an implementation, a set of implemented tests. And I was really kind of after the implemented tests in this example, mostly because providing a test implementation could just possibly be on this week's quiz. From a test requirement standpoint, this is actually a really nice and very thorough set of test requirements. In fact, it's kind of hard to think of anything else that you might do, regardless of what the code looks like. I don't know if we're covering all of those statements. I don't know if we're covering all the branches, but logically, this kind of feels like we've covered all the logical possibilities. So whacking the code, like I said, you do want to make sure that you get a decent grasp on the code issues before you take the quiz, just in case there's something like that on there. But you guys have done a really nice job in identifying the test cases. So what I have for that, all right, so here's what I did. This does not cover all of those different possibilities, and I think that all of those different possibilities are interesting. What I did was to create 3 points. I created point 1, point 2, and point 3. Point 1 and point 2 I expect to be the same as each other. Point 3 I expect to be different. And then I basically just went round robin, comparing each one against each other. So I expect point 1 to equal itself. I expect point 1 to equal point 2, but not equal to point 3. I expect 2 to equal 1 and 2 to equal itself, but 2 should not equal 3. 3 shouldn't equal 1, shouldn't equal 2, but it should equal itself. So that identity check is actually, that's an interesting case in itself that most people overlook. You could argue that that identity case automatically means that X and Y are the same, and in this case, based on the implementation, I'd agree. So there are some other cases here that we've talked about, like I don't have a case of testing equal to null. I don't have a case of specifically testing that X is different but Y is the same, or that Y is different but X is the same, or maybe I just said that the same way twice, but you know what I meant. So this doesn't actually meet all of the test requirements that you identified as good requirements, but it'll do a pretty good job of you know, examining the various possibilities. All right, so nice job on that. So next we're going to go to the Gryffindors. So Gryffindors, I know that as the last thing, it's always a little harder to get to. Did you get to the point of having a parameterized test that we can talk about?
I don't think we got to it. We had just finished up our like test equals when the breakout room closed. So we
Okay.
hadn't gotten the chance to look at it.
Okay. All right, thanks. Let me go one more on our list. How about Muggles? Have you, did you get to the point of doing parameterized testing?
We did most of it except for assert equals part.
Okay, well, let's see what you got.
So this is what we have. We followed the whatever was on the lecture slides.
Okay, so you've got a constructor here. Your constructor sets X and Y, sets X1, Y1, X1, Y2. Okay, great. And then what is the code below that? The bottom code on the left side.
This is the conditional to set the sum or is equal, sorry. Is equal.
Okay. All right. I think I get what you're going there. So let me set that aside for a minute, and I'll come back to that in a second. Let's go over to the right side. Now you've got your param, so you're setting up your parameters. So you're saying that 5, 5, and 4, 4, and it's, what's our order here? Our order is X, Y, X, Y. So X1 and X2, 5 and 5, Y1 and Y2, 4 and 4, those should be equal, right? And 5, 4, and 4, 4, that shouldn't be equal. Okay, so this looks good. All your data setup looks good. You didn't get to the assert equals. Let me go back now to the left side where I said, let me come back to that in a second, where you're talking about this dot is equal. You don't actually need to do any comparison here because you're specifying the equality. You're specifying the expected equality in your data parameters, right? That's your fifth parameter. When you look at the data sets on the right side, you've got true and false. So really all you needed to do was just save this dot is equal, right? This dot is equal equals is equal, just like you did with the X's and the Y's.
I see.
And just save that into an internal variable. And then if you wanted to implement your your assertion, what do you think that would look like?
I think we'd have is equal. Would have is equal as the first parameter. And then
Okay.
I'm not
It's all
sure.
right. Rather than writing it, just talk me through it for a moment.
Would we call point dot equal and then pass in x1, y1, x2, and y2?
Yeah, I think you're exactly on the right track here. So let me take over sharing for a moment, if I may. Is my screen visible?
Yes.
Yes.
Thanks.
Yes.
Thank you. Usually it lights up with a green border, and it didn't do that just now. All right, so here's what I've got. My constructor looks just like yours after we talked through it, right? I said this dot x1, this dot x2, or all right, my x1, y1, x2, y2, and then I saved all those, and I saved this dot is equal. Then my data looks just like your data. I chose different values, and I have a different number of them, but the structure is exactly what you had. And then, whoops, sorry. And then my test equals, where I'm doing the assertions, you were getting at this, right? In order to call equals, I have to have a point. Actually, I have to have 2 points. So the first thing I need to do is create point 1 with x1 and y1, and create point 2 with x2 and y2. And then I can verify that point 1 dot equals point 2 is equal to whatever that true or false value was. Yeah, the terms all get mixed up, right? But I'm basically checking against all of the things that I stored. And then I chose to just do another thing for free. Since I'm here anyway, and I've got these 2 points, let me check that the comparison is the same in both directions. If P1 equals P2, then P2 should equal P1. And if P1 does not equal P2, then P2 should not equal P1. So I had all this data and I thought, well, let me just get another little extra test in here and I'll test the equality in both directions. So this, I think, is exactly what you were getting at, maybe minus the both directions thing. So good work on getting through that. All right, so next, we're going to talk about, as soon as I find the right thing, I want to make sure I brief the one without the answers just yet. All right, so now we're going to talk about system testing with Cucumber. I'm going to give you my favorite example for a complex system. This system is going to come back in the end of the semester for Project 6. Project 6, Homework 6 will be about this system. So you may remember from a couple years ago now, the Boeing 737 MAX airliner, 2 of them crashed, killing 346, I think, people. So this airliner has a system on it called the Maneuvering Characteristics Augmentation System, or MCAS. MCAS is supposed to prevent the aircraft from getting its nose up too high, because if an aircraft's nose gets up too high, it loses too much speed. If it loses too much speed, it stalls. Now, in this case, stall has nothing to do with the engines not running. It means that it transitions from flying to falling. And usually falling is bad when you're an airliner. So that's what this system is supposed to do. And there were issues with this system that contributed to these 2 crashes. Note that I didn't say caused, and I'll explain why in a minute. So in our simplified version of MCAS, MCAS takes 3 inputs. Is the autopilot on or is the autopilot off? Because MCAS only operates when the autopilot is off and the pilot is hand flying, right, is flying the airplane by hand. If the autopilot is on and the computer's flying the aircraft, then MCAS shuts down because it doesn't need to do anything because the computer is already taking care of things. That's the first input. The second input is whether the wing flaps are up or down. And so if you're not an airplane, you know, an airplane fan like I am, what's a wing flap? Well, here's a picture here. You can see that when you're flying at low speed on an airliner, there are these pieces on the back end of the wing that kind of extend outward and down. And they make the wing wider and they give the wing more curve. And what they do is they generate more lift. So they allow the aircraft to fly at slower speeds. So typically these are used for takeoff and landing so that you can take off and land at lower speeds. Because really, who wants to land at 300 miles an hour, right? If you could land at like 100 miles an hour instead. So that's what the wing flaps are. If the wing flaps are lowered or down, then MCAS says, well, you must be taking off or landing, so I'm staying out of this, and it's shut off. If the wing flaps are up, then MCAS is enabled. And the last thing is what's called the angle of attack. The angle of attack is the wind relative to the wing, right? And so if normally the wing works at a pretty level, right? It flies pretty level and the air crosses over the wing at pretty level. When you're going really slow, then the air is like hitting the wing at an angle. And that angle gets bigger and bigger. And as that angle gets bigger and bigger, when it gets big enough, the wing stops flying and starts falling, right? The wing stalls when that angle gets too big. So this is not a class in aerospace engineering, so we're not going to dig into that a lot. You just need to know a little bit in order to understand the system. So what happened on these crashes? Well, the system design of MCAS has a little sensor here on the side of the nose. Here's a blow up of it. That sensor measures that angle of attack, right? It measures the angle of that wind. And on these two crashes, there were problems with this angle of attack sensor. On the Indonesian crash, this sensor had been replaced and hadn't been properly calibrated, so it was giving bad readings. On the Ethiopian Airlines crash, it is most likely that they hit a bird during takeoff, and hitting the bird sheared this thing off. And so it was giving bad readings. And so in both cases, the MCAS system thought the angle of attack was way too high. So it thought the plane was on the verge of falling. So this can happen, right? Bird strikes happen, things break, there's training involved to make sure that these things, you know, that the pilots are able to deal with these things. In this case, the training primarily consists of hitting one of these two little switches here in the cockpit, which turns MCAS off completely. Well, the reason that I said that this system didn't cause the crash is that really the crash was mostly due to flight crew errors, because the Indonesian crash, the pilots never turned the system off. In the Ethiopian crash, they did turn it off, but then they turned it back on again. So in both cases, the system was a contributing factor, but not necessarily the main factor. So here's a state diagram that kind of shows how the MCAS system works. So if the flaps are down, or the autopilot's on, or both, then MCAS is over here in the inactive state. It's not doing anything. And if the angle of attack gets too high, doesn't matter. Stays here in inactive, doesn't do anything. But if the flaps are up and the autopilot is off, then it goes into the armed state. If the flaps go down or the autopilot goes on, then it comes back over into the inactive state. Otherwise, it sits here in armed, waiting for something else to happen. So if it's in the armed state and the angle of attack goes too high, then MCAS pushes the nose of the airplane down, and then it waits 5 seconds. And if the conditions are still that way, then it pushes the airplane's nose down again. And it keeps on doing that until either the angle of attack goes back to normal and it comes back to armed, or the flaps go down or the autopilot goes on and then it goes back to inactive. So that's how this system works. Now, this is not actually the system that's on the airliners. It is a simplified example based on that. So now that we know a little bit about how this works, and I know you're like, really? Do I really understand this? It's okay. I think you probably understand enough looking at this chart. Now, the next task is to write a gherkin test. And we want to write a gherkin test that verifies that MCAS works when it's supposed to. So the scenario is MCAS activates, and you need to fill in the given, the when, and the then, right? So what's the precondition? What's the trigger? And what's the result? And then as the second part of this, which we might not get to tonight, write a test to verify that MCAS does not activate when it shouldn't. And there are a lot of possible cases here, just pick one. All right, so this chart is kind of the key to what you need to know. Any questions before we get started? This is going to be short. I'm only going to do about 8 minutes. So I think maybe we'll just focus on the first one. We won't worry about the second one in class, although I suggest that you, again, make sure you kind of understand this whole given, when, then, because it might be on the quiz. All right, questions? All right, let's dive in then. Where did my groups window go? Breakout rooms. All right, here we go. Gonna set you to 8 minutes. That'll give us just a couple of minutes to outbrief that. And here we go. I'm gonna turn this one over to the Slytherins now. So Slytherins, why don't you go ahead and walk us through what you've put together for this case?
I'll be speaking for Slytherin. So the scenario is when MCAS activate. So the given is either it's the flaps are up or autopilot is on. And then when the plane has high angle of attack, then it trims down.
All right, when given the flaps are up or the autopilot is on.
And then I also pasted
So,
it in chat.
all right, so hang on. Let's go back to the state diagram for a second. And let's check this. Do you have the state diagram handy that you can bring up? Great. All right, so the flaps are down or the autopilot is on.
The flaps are up or the autopilot is on.
The flaps are up or the autopilot is on. Okay, so if the flaps are down, we're inactive. If the flaps are up, we go to arm. But if the autopilot is on, we're in inactive.
Oh, I meant when the flaps are up or the autopilot's off.
Okay, that takes you one step closer, but not quite all the way there yet. Because your or should be in, your or should be an and, right? The flap should be up and the autopilot should be off. Because if your precondition is that the flaps are up and the autopilot is off, then your MCAS state is armed. And now you're ready for the test. But if it's or, you could still be inactive because the flaps could be up, but the autopilot could be on, right? And that would satisfy your or, but that would actually still be wrong because you'd still be over here in inactive, right? They have to both be in that condition.
Yeah, I see now.
All right, let's go back to your code for a second.
Could we say that one more time? I'm sorry, I'm not totally following.
Sure. So if we look at the state chart,
Yes.
what do we want to test?
That
I'm gonna put you on the spot here. What do we want? What do we want to test?
We want to test that the MCAS activates.
We want to test that it activates. Okay. Where do we have to be in the state in order to test that it activates?
We have to be here.
We have to be there and armed. How do we get to be in armed?
So autopilot off and flaps up makes sense to me. It's the and part that I missed.
Okay, well, if either of those are false, what if the autopilot is off, but the flaps are down? Where would we be?
Here? Is that what you're saying?
Yeah, we'd still be in inactive, right?
Okay.
So
Okay,
we need
that makes
both of those cases to be true. We need the flaps to be up and we need the autopilot to be off. And if we have that, then we're going to be in the active state. And then, let's go back to your code. Yeah, then if the angle of attack is high, then we trim down. Great. And then you also looked at the next case. MCAS does not activate when flaps down. That seems like a good case. So if MCAS is inactive and the flaps go down, MCAS remains inactive. So a more interesting test case would probably be if we're over here in inactive for any particular case and the angle of attack goes high. That's what we would normally expect to trigger MCAS to do something. But if the flaps are down or the autopilot is on, we would like to make sure that that doesn't happen. So your case might be something like, if the flaps are down or the autopilot is on, or maybe we should split that in half and say, if the flaps are down, when the angle of attack is high, then MCAS remains inactive. And then maybe another test for, given that the autopilot is on, when the AOA is high, then MCAS remains inactive.
That's just this next one, right?
Yeah, yep, exactly. Good. And then the nice thing about Gherkin is that it doesn't really matter what you want your language to be, right? There are no special words other than the given scenario, given when then. There's no special words. You can describe that however you want. And then in the implementation, you just make a matching regular expression to map that to whatever Java function it is that does whatever it needs to do. So you can have any language you want. Typically, you're going to write these using a language that, you know, your customer, your system engineer, somebody who's not a coder could read. So you wouldn't want this to read like, you know, like a piece of Java code. You'd want it to read much like what you've got here, right? Given the flaps are down. Okay, if you know your system engineer on the airliner is going to understand what it means for the flaps to be down. Your system engineer is going to understand what it means for the angle of attack to become too large or to be too high. So you've got good terminology here.
I've got a question. Is it like even in our questions here or our sentences here, we've written high AOA or AOA is high in two separate ways. Is that, it would be good to have some consistency in those, right? Is there like a structure around constants for these kinds of?
It would probably be good to have consistency, but consistency isn't necessary. And if you have a large test team working, right, if you've got 10 people building tests like this, you're going to find that you don't have total consistency. And you can deal with that in one of two ways. You can either write one matcher function and it matches AOA is high, so that when you type high AOA and try to run it, it says, I don't know what that means because I don't have anything to match it to. Or you could decide, you know what, I'm okay with lots of different ways to phrase this. And so you'd write that regular expression to match high OA, or AOA is high, or AOA is too high, or AOA goes high, or right, whatever you want. And then you can collect all of those things that mean the same thing and map it into one place. Either of them is acceptable. My gut feel is if you have a couple of definitions, that's fine. If you've got like, 10, now it seems like maybe you've just kind of gone off the deep end a little bit.
Yeah. Okay. Thank you.
All right, great. So we're actually 5 minutes later than I like to be. Still before the class technically ends, but I'm breaking my semi-promise to try to get you out at 7. So I think we're done for tonight. I will get all of these things posted. Please do understand or make sure you've gotten a little bit of experience working on some JUnit tests, and we're understanding how assertions work, understanding the given, when, then notation. If I haven't said it enough times, both of those things are on this week's quiz. The JUnit, it's a little harder to write that. I've given a little extra time. I think instead of the usual 30 minutes, I think this week's quiz is 45. So you've got a little more time to go through that and not be super rushed. Any other questions before we break?
There's an assignment due before next class, right?
There's an assignment due next class, yes.
Sure.
So that assignment is an actual pretty simple implementation of JUnit tests. And again, junit.org is your friend. That's where you'll find the downloads, and you'll find find everything you need. And I don't care what you use. My examples are on Eclipse. Eclipse seems to be increasingly old-fashioned, but what can I say? I'm an old-fashioned guy, I guess. Use that. Use Visual Studio Code. Use VI for all I care. Doesn't really matter how you choose to implement it. All right. See you next week. And discussion and questions and stuff on Blackboard is encouraged. There's a Blackboard forum for discussion about the assignment. This is again a group assignment. You get to pick your groups. You can work alone, you can work with anybody, and you can freely discuss the assignment amongst the whole class on Blackboard. And with that, I bid you a good night, and I'll see you next week.
Thank you.
Yeah.
Bye.